Hello everyone. We'd like to welcome you to this talk at the virtual conference on Data and Application Security and Privacy 2020. The following presentation will cover the topic of security enumerations for cyber-physical systems. I'm Daniel Schlette, and with me here today is Thomas Baumer.
Hello. On behalf of the other co-authors, we will present to you our research. Upfront, some information on who we are. Both of us are with the Chair of Information Systems of Professor Pernul at the University of Regensburg. Our research interests address information security and information systems. Daniel is particularly interested in cyber threat intelligence, whereas I will focus on topics of identity and access management. This should give you a quick overview. Now let's move on to the research we conducted.
To start off, here's a small motivational example. When information security experts are speaking of vulnerabilities, a conversation like the one described here is quite common.
Have you heard about the sophisticated malware?
Yes, it's described by CVE identifier CVE 2018-7522.
Do you know which IT system is affected?
Yes, its CPE name captures the category O for operating system, the vendor Schneider Electric, and its name Triconex Tricon MP3008 firmware. In addition, we are talking about version 10.
Isn't that part of our cyber-physical system?
Just now, two important security enumerations have been mentioned, namely CVE for vulnerabilities and CPE for IT assets. One can realize that they support a better understanding of what's going on and thus can lead to a better security posture. That also leads us to the idea behind our research. We adapt security enumerations to cover cyber-physical systems. Thereby, we focus on usability aspects. As can be seen on this slide here, cyber-physical systems are found in different application scenarios. For example, industrial production, healthcare, or smart cities. Our presentation is structured according to this short agenda. First, I will talk you through motivation, background, and our proposed conceptual meta model. Then, Thomas will cover a use case showing the application of our concept, and he will talk about some possible future work. So, first things first, motivation and background on CPS, as well as security enumerations. For the motivation part, one central aim of our work is the reduction of complexity within security management of cyber-physical systems. As one can clearly see, the security of cyber-physical systems is a challenging task. This is because CPS are complex and they contain numerous and heterogeneous components. In addition, there's a diverse threat landscape and attacks on cyber-physical systems are common. More recently, Mitra introduced a dedicated attack framework for ICS. Its aim is to document different attack patterns attackers use to exploit such systems. Now that we've identified a problem that is complex systems and attacks, the question is there an adequate solution? Well, security enumerations are a really good approach, but they do not yet encompass cyber-physical systems. In other domains, such as cyber threat intelligence, CTI, they build a cornerstone to cope with information security workflows and the representation of various relevant elements of security incidents. As seen on the slide here, a standardized description and a reference of given artifacts, for example, vulnerabilities. Now, moving on to the theoretical background on cyber-physical systems and security enumerations. What are cyber-physical systems? In a nutshell, cyber-physical systems relate traditional IT with physical elements. They often follow a system of system paradigm, meaning a cyber-physical system in itself can contain other systems. In addition, CPS allow real-time application scenarios based on spatial proximity. On the lower right-hand side of this slide, you can see several component types usually found in cyber-physical systems. Moving on to the security enumerations, we have two security enumerations that we cover in our work. First, Common Platform Enumeration, CPE, seen here. CPE can be used to identify IT assets. More precisely, it can be used to identify classes of IT assets. Seen in the middle of the slide, CPE as a standardized description follows a given data schema. The data schema seen here contains a CPE prefix, a version number, and multiple attributes. For the part attribute, the categories application, hardware, and operating systems can be chosen. Besides the data schema seen here, which is a formatted string, there exist two other name representation. One, the well-formed CPE name, which is a human readable and abstract concept, and the uniform resource identifier, which alongside the formatted string is used for machine readability. Maintained by the NIST, the National Institute of Standards and Technologies, CPE specification also includes a name matching mechanism, which can be used, or the CPE in general, can be used for asset inventory and vulnerability management. The second enumeration is the Common Vulnerabilities and Exposures enumeration, short CVE. It can be used to identify vulnerabilities. Each CVE entry contains a unique identifier. The structure of the identifier is seen in the middle of this slide. It contains a CVE prefix, the year the CVE entry was indexed, and a sequence number. In addition, CVE entries also contain a description and reference and additional meta information, for example, about the assigning organization and the entry creation time. Alongside this overview, there exists a JSON schema for CVE entries, which contains additional data elements. It's worth noting, CVE is maintained by Mitre. Now, that's it for the background and motivation. Now we'll move on to the conceptual meta model we propose in our work. Based on a thorough requirements analysis, we identified deficiencies in existing security enumerations. Before focusing on those deficiencies, let me state two assumptions that guide our work. First, we assume secure CPS are desirable. Secondly, we assume security enumerations are a valid solution to the problem. Now, our requirements analysis yielded two results. We found component-based deficiencies, seen here on the left-hand side. They refer to possible attack vectors. As these deficiencies, there are certain elements missing in the current security enumerations, and they refer to CPS properties and the multiple elements. And it would be good to have them covered because these elements, these properties, could be possible attack vectors. System-based deficiencies, on the other hand, address CPS systems as a whole. Therefore, they relate to the interdependent CPS components and linking vulnerabilities. Here, one can identify more relating it to the usability aspects. The core of our conceptual meta model is the extension of the existing security enumerations, namely CPE for platforms or IT assets and CVE for vulnerabilities. We extend the existing security enumerations to have a more broader coverage for the specifics of cyber-physical systems. Four characteristics are addressed by our extensions. These four characteristics can be seen in the boxes here. On the upper left-hand side, we have the technically exhaustive security enumerations. Going back, beneath each of the categories, for example, technically exhaustive security enumeration, you can see the entity type affected by our extension. So for technically exhaustive security enumeration, we extended CPE to cover additional details, for example, new attributes and new attribute values that are specific for cyber-physical systems. Recursive security enumerations address the systems of system paradigm. Here, we introduce the CPS bundle entity type to structure the multiple CPS components. Application-oriented security enumerations focus on the usability. From a security management perspective, it is most likely that a security manager only knows about certain capabilities of a cyber-physical systems or the industry sector a CPS is used in. Therefore, we extended CPE to contain these two new attributes. Lastly, coupled security enumerations address the linking of CPE and CVE. Therefore, we extend the Common Vulnerabilities and Exposures enumerations to contain references that link the two enumerations. Giving you some examples on how the conceptual meta model manifests. On the upper part of the slide, you see a traditional entity relationship diagram. It has three main entity types: CVE, CPE, and CPS bundle. Our extensions for CVE, seen here on the left, is extending the references attribute or schema element of CVE with the CPE names, allowing the coupling of the two security enumerations and their respective entries. For CPE, we introduce 5 new attributes. We introduce a sector, capability, protocol, programming language, and interface. For example, for a sector, the sector where a cyber-physical system can be used in could be transportation, healthcare, energy. For capability, a CPS has certain capabilities. In particular, its sensing elements, its sensors or sensors and actuators have certain capabilities. They can measure pressure, they can measure viscosity or other physical processes or physical elements. Certain protocols are specific to cyber-physical systems. They can be captured in the protocol attribute, for example, OPC UA. Programming language, as an example, refer to instruction lists or other programming languages common in cyber-physical systems. The CPS bundle entity type was newly introduced by our conceptual meta model. There we envision an entity type containing 3 attributes, an ID, a short description, and references to specific CPE names to document the fact that CPS contain multiple elements and they are structured in our bundle entity type.
Daniel covered with his part the background of our work and our conceptual meta model. In the following, I will evaluate our conceptual meta model with a use case. Additionally, I will outline possible avenues for future work. This picture describes our use case. You see on the left side the user who is embedded in the security management. This user is part of some organization which is visualized with the factory icon on the bottom. This organization uses a cyber-physical system with PLCs, sensors, servers, and whatsoever. However, the key point of our use case is the search engine on the top. The search engine is used by the security management and finds cyber-physical systems and its subsystems or even its subsystems. That said, let's color our use case by the Triton malware, which was mentioned in the introduction. Basically, the Triton malware targets safety instrumented systems of Schneider Electric and leverages vulnerabilities in hardware and software. There are 2 known attacks in the oil and gas sector, and it was first detected in 2017. Luckily, we didn't saw the possible destruction of physical assets because of an exploitation of the vulnerabilities. However, we saw some impact on production because of financial losses. So let's use this malware alongside with our conceptual meta model. Do you remember this slide? If not, you can make use of this video presentation, skip back to slide 13 and come back later here. By mapping our conceptual meta model to some findings of the Triton malware, you can notice the following aspects. First of all, when we searched for the CPE names of Triton to describe the malware, we didn't find them at all, so we had to create them. Additional to the plain creation of CPE names, we added the tri-station protocol and the NCM network modules, which are required to describe the Triton malware. This allows a more verbose technical description of the components like we proposed in our work. Another more verbose description of CPE names are the application-oriented extensions of CPE. Here we allow for a specification of the sector in which the components are used and the capabilities which the components possess. In our Trident example, there are the oil and gas production sector and the capabilities to be named a safety instrument. By switching to the right side of the slide, there is the recursive CPS bundle. Our conceptual meta model allows for a recursive bundling of CPE names. Therefore, we can bundle all our CPE names about Triton in a petrochemical CPS bundle, which may contain either additional CPS bundles or concrete CPE names. Finally, we want to point out that a close coupling of CPE and CVE is a requirement. The linkage between CPE and CVE needs to be done consequently, so we can query relevant CVE entries with our CPS bundle and its CPE names. With this environment, we can take a closer look at our prototype. When you kindly look at the menu bar, you can see that the prototype allows for searching CPS bundles, CPE names, and CVE entries. Additionally, you can configure their definitions as a prototypical feature, or even create new entries. For example, right now you see the controls for creating a CPS bundle on this slide. Basically, you can name the CPS bundle and add CPE names to it. On the next slide, you can see the details of a CPE name. On the left side, there are traditional CPE features, while on the right side, there are the newly added attributes by our work. Also note that you can add CVE references to the CPE at the bottom of this view. On this last slide about the prototype, you can see the overview of a CPS bundle. There you can see the associated CPE names, which are mapped to further CVE entries. So a security manager sees an overview of the currently relevant CVE entries of his own CPS bundle. That said, let's proceed to our last point, the future work. To sum up, we sense some problem in comprehensiveness and usability of security enumerations, especially when you take a closer look at cyber-physical systems. Our proposed mitigation is a conceptual meta-model for enhancing security enumerations. Therefore, future work may align this work closer within standardization efforts. Additionally, a user study is needed to determine further features which are desired by the users. Finally, the CPS bundles should be provisioned by CPS vendors, and common vocabularies of attributes should be established. There you can see a few of our references. which are required for this presentation, please check our paper for a full list of all relevant references. Finally, we want to thank you for your attention. We are looking forward to answer your questions during the virtual conference. Goodbye.